No, there isn't one where you do reactants minus
Okay,
products.
because for some reason I
But
thought-
there is something kind of related. So let me show you that real quick. These problems are really long, so I will try to formulate one that's really short.
Aren't these like the bonds?
Yes, so suppose I want to find, like, let's pick this reaction. It's an easy one. Okay, so if I wanted to find the heat given off by this reaction, I would do the products minus the reactants. I first have to find the delta H of formations. So this one's 0, this one's 0. Then you look that one up, and the value for H2O liquid is negative 286. So if I'm doing products minus reactants, I would go, okay, the amount of heat released in this reaction is 2 times negative 286 minus 0 times 2, because there's 2 moles of hydrogen, plus 0. Products minus reactants. The other way you could find the delta H of this reaction is to look at the bond enthalpies. So this method is longer because you have to calculate the energy it takes to break all the bonds, and then subtract the energy it takes to form the bonds. So it's broken minus formed. Okay, so I think of broken minus formed, and I always say since this process is a lot longer, I call this method a bunch of BF, broken minus formed. So, like if you have hydrogen, it's a single bond, there's 2 of them. So you have to look up what's the bond strength of that hydrogen. Bond energies. So that's 432, so 2 times 432 plus my oxygen bond, it's a double, so the bond enthalpy of that is 495. So you add that up and now subtract one of my bonds over here. I've got 1, 2 OH bonds. And I've got 2 of them, so what I really have is 4 HO bonds, and their enthalpy is
Last night, the screen door was unlocked.
467. So we do the broken minus the formed, you'll get the same answer, or pretty darn close. But it takes more time to like add up all the bonds, and so this way is the fast way, okay? And, you know, products minus reactants, you do the same thing for delta H and the same thing for delta G.
What are the units for delta H?
Delta H, that's a really good question to bring up. So for delta H and delta G, the units are kilojoules per mole. And for delta S, the units are joules per mole calorie. So delta S is in a different unit. So when you are doing the Gibbs free energy, you have to convert delta S into kilojoules. So you're gonna divide it by 1,000 as opposed to delta H, which is already in kilojoules. And that's another good thing to bring up. Can I erase this? So if we go back to that water reaction, and we said that the delta H of that reaction was going to be, I think it was a 2 times 286.
Negative 286.
Okay, so 2 times 286. That comes out to be negative 572 kilojoules per mole. Okay, per mole of what? So this number belongs to all 3 of these things. So the delta H of this reaction is negative 572 kilojoules for every 2 moles of hydrogen. And it's negative 572 kilojoules per 1 mole of oxygen. And it's negative 572 kilojoules for every 2 moles of water vapor. So if I were to say, if I were to give you a problem, how much energy is released by, let's just say, 20 grams of hydrogen? Though they probably wouldn't give you a mass of hydrogen, they'd probably give you a pressure and a volume and have you calculate it with PV equals nRT. So, yeah, let's just do that, that'd be simple enough. So, no, let's just stick with grams. So 20 grams of hydrogen, you would go, okay, I've got 20 grams of hydrogen. Hydrogen weighs 2.20 grams, convert it to moles, and then this is where people mess up. For every 2 moles of hydrogen, I produce that amount of energy, because this number on top doesn't change, the per mole part on the bottom does. So for every 2 moles of hydrogen, I get negative 572 kilojoules. And so that would say that if I had 20 grams of hydrogen, this is the amount of heat released. 5,636 kilojoules. That's the amount of heat released. So people forget that 2 mole part. If it was oxygen, it'd be per 1 mole. All right? Chapter 7, so there are a couple big equations here in atomic theory, and E equals HF, and depending on how they do it, sometimes F is written as the Greek letter nu for frequency. So they're the same thing, frequency, and that's not velocity, that's the Greek letter nu for frequency. The units on frequency are reciprocal seconds, or 1/seconds. Another way you can write that is seconds to the inverse. And the other real big one is equals hc over lambda. Lambda's wavelength. meters. So I think like when they ask you questions about like, does something get bigger or smaller, or increase or decrease, write the equation out. So if they have an equation that says, okay, what's the relationship between energy and frequency? If I decrease the frequency of my light, if I decrease the frequency of the light, what's gonna happen to the energy of the light? It'll decrease. It's easy to answer when you look at the equation, right? If you decrease the frequency, the energy's gonna decrease. Now, they're not gonna put the equation in the problem, they'll probably do something like, somebody was trying to get electrons to jump out of a piece of metal. And when the researcher decreased the frequency of light, more electrons were emitted. What does that say about the strength of the light? So if you decrease the frequency, you decrease the energy. And what's the, when we talk about particles of light or packets of light, do you remember the name of that? Photons. So they'll say something like, what happens to the energy of the photon? And when they say photon, they're referring to light. So what happens to the energy of the photon if you decrease the wavelength?
Increase.
It increases, yeah. So if you decrease the wavelength, so things with really small wavelengths have lots of energy. And things with really high frequencies have lots of energy. I would memorize the 8 forms of light: gamma, X-ray, ultraviolet, visible, infrared, micro, radar, and radio. What's the speed of light?
3
3
times.
times 10 to the negative 8. So
Mr. Strauss, what's the one for radio?
radar. Boy, it's hard to say how in depth they'll go here. To calculate the energy of energy level, there's an equation for that. So you've got your nucleus, you've got your energy levels, and so to calculate the energy of an energy level, it's, you don't have to memorize this you don't have to memorize it because it's there, but you just may not remember what it's for. 2.178 times 10 to the negative 18th joules over 1 over n squared. You've got, they might report it as z squared over n squared, but z is the charge on the nucleus. And you're always dealing with a hydrogen atom. So for the hydrogen atom, z is always 1. And so 1 squared is 1. N is the energy level. So the first energy level, you just plug that into your equation to find the energy. Now, if I were you, I'd go right away and multiply it by a mole, because that's usually what you have to end up to do anyhow. So if I were to calculate the energy level for the first energy level, I would plug in 1, I would multiply it by a mole, and I end up with negative 1310 kilojoules per mole. For the second energy level, I plug 2 in there, that's 2 squared is 4, so 1/4 of that times Avogadro's number. I get negative 327 kilojoules per mole. So if I want to find how much energy is released from an electron falling from this level to the next, I got one electron here that's falling. To find the energy released, I do the final minus initial. So negative 1310 minus negative 327 gives me the total energy change. So negative 1310 plus 327. So that's the energy